Hello again. In this video, we're going to begin talking about the material from section 5.4, where we're going to go over three different topics. The first one is the role that symmetry plays in integration. The second topic is the average value of a function. And then the third topic, we're going to look at the mean value theorem for integrals. But let's start with the role that symmetry plays in integrals. Okay, so first of all, let's talk about even and odd functions. A function is said to be even if f evaluated at negative x is the same as f evaluated at x. These kind of functions have symmetry about the y-axis. So here's an example of a function that's an even function. Notice it has y-axis symmetry. Now, an odd function is a function that has the property that f evaluated at negative x is actually the negative of f of x. These kind of functions are symmetric about the origin. So an example of one would be this function here is odd. And notice that it has origin symmetry. Now origin symmetry is really a rotational symmetry of 180 degrees. So if you were to rotate this part of the graph 180 degrees, it would look like this. By the way, the reason an even function is called an even function is because if you have a function that looks like x to the n power, then if n is an even integer, 2, 4, 6, 8, 10, 12, and so on, then that's an even function. But if it's an odd power, like 1, 3, 5, 7, 9, and so on, then this would be an odd function. Okay, so having said that, let's look at the role that integrals play with respect to this idea of even and odd functions. So let's suppose you wanted to find the definite integral from minus a to a for this function here. Now, since it's an even function, notice that this definite integral gives you the area that's trapped between the function and the x-axis starting at negative a and ending at a. Notice that the area on this side of the graph is equal to the area on this side of the graph, and that's because it's an even function. It has this y-axis symmetry. And so you could find the area on this side from 0 to a, and then just double that amount of area to get the area from minus a to a. So that's because it's an even function, though. Now for an odd function, the definite integral from minus a to a of an odd function would end up being 0. And that's because, remember, this gives you the net area that's trapped between the function and the x-axis. And notice that here you get a positive contribution, over here you get a negative contribution, and of course those cancel out to 0. Okay, so this is all stated in Theorem 5.4. It says let a be a positive number and let f be an integrable function on the closed interval from minus a to positive a. If f is an even function, then this definite integral from minus a to a of f of x is the same as 2 times the definite integral from 0 to a of f of x. And if f happens to be an odd function, then this definite integral from minus a to a of f of x actually equals 0. Okay, so let's look at an example where we use this theorem. So let's say you wanted to find this definite integral. Okay, first of all, we can break this up across subtraction into 2 definite integrals. So it's this definite integral minus this one. Then you can pull the 3 out since it's a constant. And then notice here that you have an even function, and here you have an odd function. And so this part here, since this is an odd function, now, of course, you have to go from minus a to a, right? So this goes from minus 2 to 2, okay? But as long as that happens, and this is an odd function, then we know that we get 0 because we get a positive contribution and a negative contribution. Cancel out. Okay, so we know this definite integral is going to be 0. This one, we know that it's twice the definite integral from 0 to 2 of x to the fourth. And that's because this is an even function. Okay, and so let's just find out what the area is trapped in here. By the way, if you graph this function, x to the fourth looks something like this. And we're finding the area between 0 and 2. So the area in here. Okay, and then because of the symmetry of this problem, that's the same amount of area that's trapped in here. So we're finding the area in here from 0 to 2, and then we're just doubling it. Okay, so notice x to the fourth is continuous on this closed interval from 0 to 2. So by the fundamental theorem of calculus, all we need to do to evaluate this definite integral is to find any antiderivative of x to the fourth. And then we're going to evaluate that definite integral at the upper limit and then subtract what we get when we evaluate it at the lower limit. Okay, so a definite integral for this, an antiderivative of this would be x to the fifth over 5 plus any constant. We just need any antiderivative, so the most convenient one would be when the constant's equal to 0. So let's just use that one. Okay, so we end up with f evaluated at the upper limit minus f evaluated at the lower limit, and then all times 2. Okay, so f evaluated at 2 is 2 to the fifth over 5. And then f evaluated at 0 would just be 0. So 2 to the fifth would be 32. So this is 32 over 5. And then times 2, that would give you 64 over 5. And that's the total area trapped between minus 2 and 2, between the function and the x-axis. Okay, so that's an example where we would use the symmetry of these functions to help you evaluate these definite integrals. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.